What if the universe we've always believed we understood turns out to be something we barely understand at all? For decades, scientists were confident in a simple idea: the deeper we look into space, the further back in time we see, and the earlier the universe was, the simpler it should appear. A young universe was expected to be dark, small, and only beginning to form its first structures. But the James Webb Space Telescope is quietly challenging that assumption. When Webb looks into the earliest chapters of cosmic history, it does not see a fragile universe struggling to take shape. Instead, it reveals massive galaxies, intense energy, and complex structures appearing far earlier than our theories ever predicted. What should look like the universe's childhood instead looks unsettlingly mature. It feels as though the universe skipped steps, growing up faster than it was ever supposed to. James Webb was built to study the universe's beginnings. Yet what it is uncovering is not just new data, but deep contradictions. These are not isolated surprises or minor errors. They are discoveries that ripple through cosmology, forcing scientists to re-examine timelines, formation processes, and the basic assumptions we use to describe reality itself. Stay with this journey until the end, because what begins as a series of unexpected observations slowly becomes something far more disturbing. Each layer raises the same question with greater urgency. What if the way we've been reading the universe has been wrong all along? Sometimes the hardest thing is not what the universe is telling us, but admitting that the instrument speaking for it is precise enough that we can no longer look away. So before we follow James Webb out into those unsettling distances, we have to sit with what it is, and why its word carries so much weight. This telescope is not a lucky accident or a speculative prototype. It is the end result of decades of argument, redesign, cancelled meetings, resurrected budgets, and an international decision that, if humanity was going to build a single machine to question its story of the cosmos, it would be this one. NASA led the mission, but the European and Canadian space agencies are full partners. The mirror segments, instruments, launch rocket, and operations are stitched together from work spread across continents. It helps to remember the scale of that decision. The project's lifetime cost is on the order of $10 billion, spread across many years, with NASA carrying most of it and Europe and Canada contributing launch services and key instruments. You do not quietly spend that much, over that long, on a toy. You do it on something that is expected to change the baseline of what we know. James Webb was launched on a European heavy-lift rocket from the equator in South America, on a December morning when the weather, the trajectory, and thousands of tiny checklists finally lined up. It did not go into orbit around Earth the way many satellites do. Instead, it was sent far beyond the Moon, toward a place in space where gravity and orbital motion balance in a very particular way. A Lagrange point called Sun-Earth L2. A Lagrange point is not a physical object. It is more like a location in the invisible geometry of gravity, where the pull of Earth and the Sun combine so that a spacecraft can orbit the point itself. Webb does not sit precisely at L2. It loops around it in a gentle halo orbit, always keeping its vast sun shield between its mirrors and the Sun, Earth, and Moon. That constant shielding lets the telescope stay incredibly cold and stable, which is essential for what it is built to see. Unlike Hubble, which is most comfortable in visible light, the kind our eyes see, Webb is tuned mainly to infrared light. Infrared is light with longer wavelengths than red, the kind of light we feel as warmth on skin but do not see with our eyes. In practice, that means two crucial things. It can see through dust that blocks visible light, and it can catch the ancient, stretched out light from very distant galaxies whose glow has been shifted from visible into infrared by the expansion of the universe. To do that well, it needs to be both large and cold. The primary mirror is a honeycomb of 18 hexagonal segments made of beryllium, a stiff, lightweight metal, each coated with a thin layer of gold that reflects infrared especially well. Together they form a mirror about 6.5 meters across, more than twice the diameter and over 6 times the light collecting area of Hubble's primary mirror. That extra area matters. The larger the mirror, the fainter and more distant the objects it can detect. All of that mirror had to be folded to fit inside the rocket, then unfolded flawlessly in space. After deployment, engineers spent months nudging each segment a tiny distance at a time, using actuators that can move the metal in steps smaller than the width of a human hair. The goal is to make all those separate pieces behave as if they were a single, smooth surface. NASA once explained that if the primary mirror were the size of a continent, the segments would have to be aligned to within a fraction of the thickness of a coin. That is the level of care behind every photon of light that reaches Webb's detectors. But the mirror is only the beginning. Behind it sit 4 main scientific instruments, each with a different way of listening to the universe. There is a near-infrared camera, NIRCam, that produces the sharp, deep images people now recognize in headlines. There is a near-infrared spectrograph, NIRSpec, which does something quieter, but in many ways, even more important, it takes the light from many objects at once and spreads it into spectra. The detailed rainbows where absorption and emission lines reveal what atoms and molecules are present, how fast things are moving, and how far away they are. Another instrument, MIRI, works at longer, mid-infrared wavelengths. That range is crucial for seeing colder things, dust clouds where stars are forming, faint glow from molecules in exoplanet atmospheres, and the hidden, warm cores of galaxies wrapped in their own soot. Finally, NIRISS and the fine guidance sensor share a package. NIRISS can do specialized imaging and spectroscopy, including modes designed for exoplanets, while the guidance sensor keeps the whole observatory locked onto its targets with exquisite steadiness. Words like spectrograph and imager can sound abstract, but in practice they mean this. Webb is not just taking pictures, it is reading barcodes of light. Every bump and notch in a spectrum is a clue. Some lines tell you that water vapor is present, others announce carbon dioxide, methane, or neon. Some reveal how fast a galaxy is moving away from us, stretched by cosmic expansion. Others show how hot a star-forming region is, or how many heavy elements a galaxy has already built. When scientists say Webb discovered something, what they usually mean is that the patterns in those spectra left them with no honest alternative explanation. Because of its size and wavelength coverage, Webb can see galaxies so distant that their light left them when the universe was only a small fraction of its current age. NASA's own mission pages emphasize that one of its core goals is to look back to when galaxies were young, more than 13 billion light-years away. That is not marketing language. It is baked into the telescope's design. The telescope's environment is tuned with the same severity. The multi-layered sun shield, always facing the sun, lets the mirror and instruments cool to tens of degrees above absolute zero, cold enough that Webb's own heat does not drown out the faint infrared glow it is trying to detect. The orbit around L2 avoids even brief eclipses by Earth or the Moon, because even a short dip into shadow would change the thermal balance and, with it, the measurements. And then there is the way Webb is used. It is not a private observatory held by a small group. Astronomers around the world write detailed proposals explaining exactly what they want to observe and why. Those proposals are peer-reviewed, ranked, argued over, only a fraction win telescope time. And every hour is carefully planned. The point is that when Webb stares at a patch of sky for many hours, it is doing so because a group of experts convinced other experts that this was one of the best uses of a precious, finite resource. After the observations are taken, raw data flows down through the deep space network, is processed and calibrated by teams at the Space Telescope Science Institute, and is then handed to the scientists who proposed the work, with the understanding that, after a proprietary period, the data will become public. Before any startling claim makes its way into a press release or a paper, it has passed through a chain of instrument specialists, calibration checks, and independent analyses. Mistakes can still happen, of course, but noise and glitches do not usually survive that many skeptical eyes. All of this is why, when Webb shows us something that does not fit, people pay attention. It is an instrument designed to see the faintest, oldest, most dust-hidden structures in the universe, built by thousands of specialists, operating in a carefully controlled environment, using techniques refined over generations of space astronomy. It was never meant to flatter our expectations. It was meant to test them, so when that cold, gold mirror looks back toward the first light and sends down an image or a spectrum that seems, at first, impossible. The question is not, did the telescope make a mistake? The question is, what, exactly, are we wrong about? To even begin to answer that question, we have to remember the quiet assumptions we carried for so long that they stopped feeling like assumptions at all. We had a story of the universe that felt simple enough to live with, even if the equations behind it were anything but simple. The story went like this. Long ago, the universe was smaller, denser, and hotter than anything we can really imagine. Space itself was compressed. Matter and light were tangled together in a bright, opaque fog. As space expanded and cooled, that fog thinned. Light finally slipped free and has been crossing the universe ever since, slowly stretched into longer wavelengths by the expansion of space. When we look out and see the faint microwave glow that fills the sky in every direction, that is the fossil light from that early moment, cooled from blinding brightness to a whisper. From that point onward, the idea was straightforward. If light takes time to travel, then looking far away is the same as looking back in time. A nearby galaxy shows us the recent universe. A distant, faint smudge shows us an earlier chapter. If we could look far enough, we would see younger and younger structures, until eventually there would be almost nothing at all. In this picture, the early universe is a place of smallness and delay. Gravity is there from the beginning, always tugging, always trying to pull matter into clumps. But gravity works slowly when things are spread out. It has to fight against the expansion of space, which is constantly stretching the distances between everything. You start with tiny ripples in density, slightly more matter here, slightly less there. Over vast stretches of time, those tiny differences amplify. The slightly denser patches pull in more material, becoming clouds. Those clouds collapse into the first stars. Collections of stars become the first small galaxies. Many of those galaxies later merge into larger ones. It is like watching droplets gather on a window. At first, there are only scattered beads of water. Gradually, they slide and meet and form larger shapes. Nothing big appears suddenly. It is all accumulation, step by step. Astronomers turned that story into a working model. They filled in details with simulations, with careful measurements of how galaxies are distributed across the sky, with studies of the cosmic microwave background, the afterglow of the early universe. They gave this framework a name that sounds more dramatic than it feels in equations, the Standard Model of Cosmology, often called the lambda cold dark matter model. The word lambda there is shorthand for dark energy, the mysterious effect that seems to be accelerating the expansion of the universe. Cold dark matter refers to invisible matter that does not emit light and moves slowly compared with the speed of light, acting as a kind of gravitational scaffolding. That scaffolding is crucial. Dark matter, as far as we can tell, interacts mainly through gravity. It does not glow. It does not collide and heat up the way ordinary gas does. But it clumps. In the young universe, as tiny fluctuations in density grow, dark matter collapses into halos, roughly spherical regions where its gravity dominates. Ordinary matter falls into those halos. Gas collects there, cools, and eventually forms stars. In that sense, galaxies grow inside dark matter, halos like cities growing along a hidden, invisible landscape. Within this picture, certain expectations follow naturally. If you look back to a time when the universe was still very young, you should mostly find small dark matter halos, small clumps of gas, small, dim galaxies. Those galaxies should have relatively low masses in stars. Their light should be dominated by young, hot stars that have not yet had time to enrich their surroundings with heavy elements. Their structures should be messy and irregular, not the graceful spirals and large, smooth, elliptical shapes we see nearby. Bright, massive galaxies and huge clusters should appear later. After many mergers and long periods of star formation, there is another expectation hidden in the chemistry. In the earliest times, the universe should be simple in composition, mainly hydrogen and helium, with traces of lithium and almost nothing else. All heavier elements, like carbon, oxygen, nitrogen, silicon, iron, are made later, inside stars. Those stars live their lives, fuse lighter elements into heavier ones in their cores, and then eject those elements back into space, either in gentle winds or in violent explosions. New generations of stars form from this enriched gas. When we see heavy elements in a galaxy, we are really seeing evidence that there have already been multiple generations of stars. That takes time. So, if we look far back, toward the first galaxies, we expect them to be chemically primitive. Their gas should be nearly pristine. Any heavy elements should be present in tiny amounts. The older and more processed the galaxy, the more of those elements we should find. In other words, enrichments in oxygen or iron are a kind of clock. More enrichment usually means more time has passed. A similar timing logic applies to black holes. The giant black holes we see in the centers of many galaxies today did not appear at full size. In the standard story, they start as remnants of massive stars or as slightly heavier seeds that form in dense regions, then grow by swallowing gas and sometimes by merging with other black holes. But this is not instant. There is a limit to how fast a black hole can grow by accreting matter, because if it pulls in gas too quickly, the radiation from the hot gas pushes back and slows the infall. This sets a natural pace. To reach the huge masses we see in the present universe, even a black hole that grows as fast as possible needs a long time. All of this leads to a simple intuition. The younger the universe, the smaller, dimmer, and more primitive its structures should be. If you could line up snapshots of the cosmos at different ages, you would imagine a smooth progression. First, a nearly uniform fog, then slight speckling, then small galaxies in disarray, then more organized structures, then the rich, clustered web we see around us today. Astronomers turned that intuition into concrete predictions. They ran numerical simulations in supercomputers, evolving billions of particles that represented dark matter and gas under the laws of gravity, hydrodynamics, and cosmic expansion. These simulations start from conditions that match the tiny fluctuations seen in the cosmic microwave background and then march forward. By the time the simulated universe reaches an age similar to the present, the distribution of galaxies in the simulation looks remarkably like what surveys have actually mapped in the sky. That gave people confidence that they were on the right track. From these simulations and from analytic calculations, they estimated how many galaxies of a given brightness and mass should exist at different times. They estimated what fraction of hydrogen in the intergalactic medium, the thin gas that fills the space between galaxies, should be neutral and what fraction should be ionized, meaning its electrons have been stripped away by energetic photons. This transition from a mostly neutral universe to a mostly ionized one is called reionization. It is thought to be driven mainly by the ultraviolet radiation from early stars and galaxies, possibly helped along by the radiation from early quasars, which are bright, actively feeding black holes. The period before this transition, after the universe has cooled enough for hydrogen atoms to form, but before enough stars have ignited to light things up, is sometimes called the cosmic dark ages. During that time, there is no obvious visible light shining, no stars yet, only the fading afterglow and the slow growth of invisible structure. In the old rules, this phase is a long, quiet prelude. By the time reionization is largely complete, there should be many more galaxies, but most of them should still be quite small. The ones that dominate the production of ionizing photons are expected to be low-mass systems, faint by present-day standards, but numerous. Their combined output acts like many small campfires, gradually illuminating a foggy landscape, rather than a few bonfires instantly clearing the night. This picture also carries a built-in idea of cosmic patience. On human timescales, 1,000,000 years already sounds like forever. In this story, 1,000,000 years is a brief interlude. Stars live for millions to billions of years. Galaxies assemble over billions. The universe does not rush. Structures emerge slowly, as if the cosmos were taking its time, layering process upon process. And because all of this is encoded in equations, astronomers came to trust that, within this framework, the early universe might be unfamiliar, but it would not be outrageous. It would obey the same rules we infer from what we see around us now, just extrapolated back. There might be details to fill in, but the overall rhythm, slow gravitational growth, gradual chemical enrichment, delayed appearance of complexity felt secure. So when telescopes looked deeper and deeper, first from the ground and then with Hubble, the images seemed to support this narrative. The most distant galaxies Hubble could detect were faint, often compact, often irregular. There were hints of surprising brightness here and there, but within the uncertainty of the data, the old rules held. It was easy to believe that, if we just pushed a little further, we would finally see the universe as it was in its childhood, small, dim, and just beginning to build. That was the expectation James Webb inherited. Not because scientists lacked imagination, but because, given what they knew, this was the cautious, conservative picture. Light from more distant galaxies would be redshifted into the infrared, stretched by cosmic expansion, and eventually become too faint for Hubble to see. Webb, with its larger mirror and infrared vision, would extend that reach. It would fill in missing details, add clarity, refine timelines. What almost no one expected was that, when Webb finally opened that new window, the universe would not look like a child at all. It would look, in many ways, disturbingly grown. It did not take long for that unease to turn into something sharper. Once the first deep fields began to arrive, one of the earliest things Webb did was something deceptively simple. It stared. It fixed its gaze on a patch of sky that, to ordinary eyes, looks almost empty. No bright stars, no obvious galaxies, just a bare piece of darkness. Telescopes have been doing this kind of thing for years. Hubble's deep fields became famous for exactly that reason. You point at what looks like nothing, wait, and let the faintest light slowly build up. When you finally process the data, the nothingness falls apart into a crowd of galaxies, each one a separate island of stars. Webb repeated that trick, but with some crucial differences. Its mirror is larger, so it drinks in more light. Its eyes are tuned to infrared, so it can see the stretched, reddened glow from very distant galaxies that Hubble misses, and it can hold that stare for longer, stacking exposure upon exposure until photons that have been traveling for most of cosmic history finally reach its detectors. On the screen, the first processed images did what everyone expected. They were beautiful in the quiet way astronomers appreciate, a field of tiny smears and specks, each one a galaxy. Some diffuse and ghostly, some sharp and compact. But when teams began to measure how bright those galaxies were and how their light was distributed across different colors, something in the numbers refused to sit down and behave. This is where the term redshift becomes important. Redshift is a way of describing how much the light from an object has been stretched to longer wavelengths by the expansion of the universe. The more distant a galaxy is, the more its light has been stretched, the redder it appears, and the larger its redshift. In practice, astronomers use redshift as a proxy for time. Higher redshift generally means earlier in cosmic history. There are two main ways to estimate redshift. One is photometric. You measure how bright a galaxy is in several filters, each filter letting through a narrow range of wavelengths. And then you fit models to that pattern of brightness. Certain features in a galaxy's spectrum, like the abrupt drop in light produced when neutral hydrogen absorbs photons above a particular energy, leave fingerprints in those patterns. The other way is spectroscopic. You take the light from that galaxy and split it into a detailed spectrum, looking for specific emission or absorption lines whose rest wavelengths are known in the laboratory. The amount by which those lines are shifted tells you the redshift directly. Photometric estimates are faster and can be done for many objects at once, but they are less certain. Different combinations of dust, star formation history, and age can sometimes mimic each other. Spectroscopic measurements are slower and technically harder, but they are much more secure. In the early days of Webb, both methods began to sing the same unsettling theme. Teams looking at the first deep images saw galaxies that appeared not just faint and distant, but surprisingly bright for their apparent distance. When they estimated redshifts photometrically, many of those objects seemed to belong to an era when, according to the old expectations, the universe should have hosted mostly small, dim, chemically simple systems. Instead, they were seeing candidates that looked massive, compact, and in some cases already quite complex. At first, it was easy and responsible to suspect the method. Maybe the models used to estimate redshifts were not quite right in this new regime. Maybe the galaxies had unusual dust properties, or odd star formation histories, that tricked the fitting codes into thinking they were farther away than they really were. That is the conservative instinct in astronomy. Mistrust the interpretation before you, mistrust the universe. But then, spectrographs like NIRSpec and other instruments started to do their slower, more surgical work. They collected light from some of the most promising candidates and spread it into detailed spectra. In those spectra, emission lines from elements like hydrogen and oxygen appeared, sharply displaced toward longer wavelengths. When researchers measured those shifts, they confirmed that at least some of these galaxies were genuinely from very early times, when the universe was still young by its own standards. This is where the phrase, "galaxies that should not exist yet," began to show up in discussions and in more public writing. It is not that the laws of physics forbid galaxies at such early times. Gravity does not switch on suddenly at a chosen age. But, within the standard model, the combination of expansion history, dark matter growth, and star formation efficiency all conspire to make the rapid assembly of very massive, very bright systems at such early epochs extremely unlikely. To grasp why, imagine again that forest planted not long ago. If someone tells you the seeds went into the ground a few years back, you expect saplings, thin trunks, short branches. You might allow for a few odd cases, perhaps one or two fast-growing species that are taller than the rest, but you do not expect to find towering, ancient trees with thick bark and tangled crowns. What Webb seemed to be revealing in some of those early fields was the cosmic equivalent of those towering trees. Galaxies whose brightness implied large numbers of stars already in place, packed into relatively small regions. Their inferred stellar masses, even allowing for uncertainties, were higher than comfortable models like to allow for that age. Their light sometimes showed not only young, hot stars, but signs of more complex populations. This tension was not just about individual record holders. It was statistical. When teams counted how many bright galaxies appeared at those early times and compared that count with predictions from simulations, they found an excess. There were more luminous galaxies than expected. Not an infinite number, not an absurd flood, but enough to say, this is not just a rare fluke. Something in the way we think galaxies grow, or in how we are reading this light, needs to be reconsidered. The possibilities split into two broad paths. One path says, perhaps we have misjudged how efficiently galaxies can form stars under early conditions. If star formation can proceed in brief, intense bursts, or if the first generations of stars were, on average, more massive and luminous than stars forming today, then a galaxy could appear very bright, while still being less massive than naive models suggest. In that scenario, the apparent maturity is partly an illusion of light, not of mass. The other path is more radical. It suggests that perhaps the backbone of the model itself, the way dark matter halos grow, the way the expansion history unfolds, the assumed properties of dark matter and dark energy may need adjustments. Not a complete rewrite of cosmology, but a shift in some of its parameters or assumptions, such that structure can form more quickly or more efficiently than we thought. Most working cosmologists lean toward the first kind of explanation, at least as a starting point. It is less reckless to say our models of star formation under extreme conditions are incomplete than to say our entire picture of cosmic history is wrong. We already know that star formation is a messy, feedback-filled process even in the nearby universe. Massive stars pump energy and momentum into their surroundings, stirring and dispersing gas. Black holes, when they feed, can power jets and winds that either quench or trigger new waves of star birth. Translating all of that chaos into clean prescriptions in simulations is hard, but the discomfort does not go away. Even if you push star formation toward its more extreme plausible limits, some of the galaxies Webb is seeing still sit near the edge of what the models can handle. And each time, a spectroscopic confirmation pins down a redshift firmly, the room for hand-waving shrinks. There is also a subtle psychological effect at play. For decades, astronomers have lived with a kind of comforting distance between their equations and the most radical implications those equations might have. The models said the first galaxies would form at a certain time, with certain properties. But because no telescope could see that far back with clarity, those statements lived in a safe, speculative space. They were extrapolations, honest and disciplined, but still projections thrown onto a screen no one could fully inspect. Now that screen has been peeled back. Webb is looking directly into the regime that, until recently, existed only in simulations and rough estimates. The universe, it turns out, does not feel obliged to conform to our sense of what is tidy or reasonable. Some of these galaxies appear not just bright but compact, their light concentrated into very small angular sizes on the sky. That compactness matters. A sprawling, diffuse object can hide all kinds of substructure. A tight, Intense one suggests a lot of mass gathered in a small volume, or at least a lot of light. When Webb's instruments tease out their shapes, some look like simple blobs. Others already show hints of clumpiness or even elongated structures, as if the cosmic web is sketching filaments earlier than expected. A few show signs that something energetic may be happening in their cores. Light that is harder, more weighted toward high-energy photons, or emission line ratios that hint at the presence of active galactic nuclei, the glowing surroundings of feeding black holes. If that is the case, then these are not just early galaxies. They are early galaxies with engines already switched on at their centers, pouring radiation into their environments. All of this does not mean we have been entirely wrong. The broad strokes of the standard cosmological model still fit many lines of evidence well, but these impossible galaxies act like splinters in the mind. They irritate. They force revisions. They suggest that the actual universe may have chosen, in at least some places and times, a more aggressive route to complexity than our cautious theories allowed. And so people go back to their tools. They refine the algorithms that fit photometric redshifts. They improve the simulations, pushing resolution higher, adding more careful treatments of the way gas cools, fragments, and forms stars under extreme conditions. They test alternative explanations. Maybe some of the candidates are contaminated by nearer objects that happen to align along the line of sight. Maybe gravitational lensing, the bending and magnifying of light by massive foreground structures, is making a few galaxies look brighter than they truly are. Some of those checks succeed in deflating the tension. A few candidates turn out not to be as distant as first thought. Others lose some of their inferred mass when new models of their stellar populations are applied. But enough of them remain problematic to keep the conversation alive. The sense that there are galaxies out there, seen as they were when the cosmos was still young by its own measure, that already look too rich, too dense, too switched on. What makes this especially unsettling is not just the presence of anomalies, but when and where they appear. These are not oddities lurking in some obscure corner of parameter space. They sit close to the era we have long called the cosmic dawn, the time when the first significant populations of stars and galaxies are thought to emerge from the dark. To find such apparent overachievers, there feels a bit like walking into a kindergarten classroom and discovering not just one precocious child, but an entire row of them calmly solving university-level problems. You could, of course, shrug and say, the universe is big, unlikely things happen. And that is true. Rare events will occur somewhere. But science is about patterns, not isolated curiosities. When the pattern starts to look systematic, when the number of early bright galaxies seems consistently higher than the sober models predict, the shrug stops being an option. In the end, that is what makes these galaxies feel as though they should not exist yet. Not that there is a rule carved into the fabric of physics forbidding them, but that our stitched-together story of how gas falls into halos, how stars ignite, how feedback regulates growth, and how long all of that takes, does not easily make room for them. They sit slightly ahead of schedule, like characters who walk on stage before their cue. And as with any good story, once a character ignores the script, you start to wonder what else in the play is not as under control as you thought. It is only when you start questioning who gave the cue that you realize the script of the universe is written in equations as much as in light. For a long time, those equations seem to agree with us. The standard picture of cosmic time is, on paper, almost reassuring. There is a beginning, not in the sense of a fireball exploding into empty space, but in the sense of a moment when space itself was extremely hot, dense, and rapidly expanding. From that moment, the universe cools and stretches. Radiation thins. Matter clumps. Stars ignite. Galaxies grow. If you know the laws of gravity, the composition of the universe, and the rate at which it expands today. You can integrate those equations backward and forward, and they will tell you how much time lies between different eras. In that picture, each redshift does not just mark a color shift, it marks a timestamp. A galaxy at a given redshift belongs to a specific chapter of cosmic history. The higher the redshift, the earlier the chapter, the less time the universe has had to assemble whatever you are seeing. When astronomers talk about the age of the universe, they are not guessing. They combine measurements of how fast space is expanding now with the patterns frozen into the afterglow of the early universe, the cosmic microwave background. From that, they infer that the universe today is on the order of a little under 14 billion years old. That number is not perfect. There are tensions in the details, but it is stable enough that entire fields of astrophysics have been built, assuming it is roughly right. From there, you can turn the handle and ask, how old was the universe when light left a galaxy at a certain redshift? The answer is always less than its age today, often far less. At some of the extreme redshifts where Webb is now finding galaxies, the universe would have been only a small fraction of its current age, hundreds of millions of years old rather than billions. This is where the paradox begins to sharpen, not in the images themselves, but in what we infer from them. Galaxies are not just blobs of light. Their colors carry information about the mix of stars inside them. Young, massive stars shine fiercely in blue and ultraviolet light. Older, cooler stars glow more softly in red and near-infrared. Dust absorbs and scatters some wavelengths more than others. When you model all of that together, you can estimate what kind of stellar population best matches the light you see. Those models, called stellar population synthesis models, are our attempt to simulate what an entire city of stars looks like when you cannot resolve its individual buildings. They take into account things like the initial mass function, the statistical distribution of star masses when a new generation is born, and how stars of different masses age and die. By comparing a model spectrum with the observed one, you can estimate not only how many stars are present, but how long ago major episodes of star formation must have started. If you do this for a nearby galaxy, the numbers generally make sense. You may find evidence of bursts of star formation at different times. You may find that a particular population of stars is a few billion years old, another younger. All of that fits comfortably within the overall age of the universe. But when teams began to apply similar techniques to some of the early galaxies seen by Webb, at redshifts where the universe itself was still very young, they sometimes obtained answers that felt uncomfortably close to, or even apparently older than, the allowed cosmic time. It was as if you entered a town that had been founded by reliable records 10 years ago, and yet some of the trees on the main street seemed to carry growth rings, suggesting they had been alive for 20. No one takes those implied ages at face value. The paradox is not that we literally believe a galaxy can be older than the universe. The paradox is that, to make the numbers fit, you have to start stretching the assumptions in your models harder than you would like. Maybe the stars in those galaxies formed in an unusually intense, rapid burst not long before we are seeing them, so that the light mimics an older population. Maybe the dust is tricking us, reddening the light and making it look more evolved than it really is. Maybe the initial mass function is different under early universe conditions, favoring more massive stars that evolve quickly and change the integrated light more dramatically. Every maybe is a signal. The math that once felt straightforward is now balancing on a growing stack of conditional phrases. Behind these fits and models lies the more basic timing argument. To assemble a certain mass of stars, you need fuel, gas, and time to turn that gas into stars. Star formation is not perfectly efficient. A cloud does not convert all of its mass into stars in one go. Some gas is blown out by feedback from young stars and supernova explosions. Some settles, cools, and later forms new generations. The rate at which all of this happens is constrained by basic physics. how fast gas can cool, how quickly it can lose energy and collapse, how strongly it is stirred and heated by the very stars it is trying to make. If a galaxy appears to host an enormous number of stars at a very early time, you can ask, how quickly must it have been forming those stars to reach this point? Did it have to begin almost as soon as the universe allowed the first clouds to condense? Did it have to sustain an extreme rate of star formation? Nearly as fast as the equations allow. For most of its life so far, there is a limit to how often you can answer yes to questions like that before the pattern starts to look suspicious. In any one case, you might be seeing an outlier, a rare, especially efficient system. But if many galaxies appear to be pushing against the same timing boundaries, you are no longer dealing with a few exceptional prodigies. You are dealing with a curriculum that might be wrong. The paradox is not only about stars, it extends to chemical signatures. When Webb spreads a galaxy's light into a spectrum and finds clear lines from elements heavier than helium, especially in fairly high abundances, it is seeing the fossil record of stellar generations already gone. Those heavier elements are forged in stellar cores and released in supernovae and winds. Their presence in large amounts implies that massive stars have lived out their short lives, exploded, and shared their products, and that new stars have formed from that enriched gas. Each of those cycles takes time. The more enrichment you see, the more cycles you are forced to pack into the short window between the birth of the universe and the moment the light we are now receiving left that galaxy. The math does not say it is impossible. It just starts to look as though the early universe had far less idle time than we once imagined. So when people talk about a timeline paradox, they are pointing at this mismatch between the tidy, gradual picture drawn by basic cosmology and the compressed, accelerated narratives implied by some of Webb's observations. The equations that once made the universe feel like a patient, slowly unfolding story now have to accommodate a version of history in which major structures and complex chemistry appear in what feels like fast forward. It is important to be honest here. There are many ways to soften the paradox. Astronomers are revisiting the ingredients of their models, the way dust behaves at early times, the mix of stellar masses, the shapes of galaxies we cannot quite resolve. They are carefully checking for biases introduced by the way surveys select their targets. They are looking for hidden, active galactic nuclei, central black holes whose energetic surroundings might contribute a lot of light and masquerade as starlight. Bit by bit, these efforts chip away at the sharpest edges of the tension. Some galaxies move back into safer territory once better spectra are obtained. Some of the most extreme age estimates shrink when newer models, tuned for the harsh conditions of the early universe, are applied. The universe, it turns out, is generous with opportunities to mislead. And yet, the feeling remains that we are, at the very least, being asked to rethink our sense of cosmic scheduling. What we used to describe as a long dawn, a gentle brightening from darkness to complexity, now looks more like a sudden, rapid ignition in certain places. The first stars may have formed earlier than we assumed. Star formation in some halos may have been astonishingly efficient. The early cosmic web may have funneled gas into dense regions with ruthless focus. There is a quiet discomfort in realizing that the math has not failed. But our use of it may have been too narrow. The equations of general relativity still describe how space and time respond to matter and energy. The basic nuclear physics inside stars has not changed. But the way those pieces combine, under the specific initial conditions of our universe, may not follow the most modest path we drew on the chalkboard. Part of the unease comes from how deeply we rely on the idea that time, on cosmic scales, gives us room. Room for gradualism. Room for incremental change. When Webb shows us galaxies whose inferred histories almost run out of that room, it is less a direct contradiction and more a reminder that even billions of years can, under the right pressures, feel cramped. The paradox, then, might be less about the universe and more about us. About how much we want reality to move at a pace that feels reasonable, that spreads events in a way our minds can comfortably map. Webb's timelines do not always grant us that courtesy. They suggest that the universe, left to its own devices, may choose to do difficult things quickly, without waiting for us to prepare a theory that makes those things feel gradual. And as we sit with that possibility, another, quieter question begins to form beneath the equations. If our sense of when things are allowed to exist can be wrong, what else in our picture of reality is gently, persistently out of sync with what is actually there? Nowhere does that unease feel sharper than when the universe pours all its light into a single point and dares us to ask what could possibly be hiding there. Quasars are what you get when gravity and hunger meet at the center of a galaxy. The word itself is a shortening of quasi-stellar radio source, a historical name, from a time when astronomers saw bright, star-like points in the sky whose light did not behave like starlight at all. When they split that light and measured its spectrum, they realized these objects were not stars in our own galaxy, but the blazing hearts of galaxies far away, powered by something unimaginably compact and powerful, supermassive black holes feeding on their surroundings. A black hole, by itself, is dark. It is the matter around it that screams. Gas falling toward a black hole does not simply vanish. It spirals inward, forming a flattened whirlpool called an accretion disk. Friction and magnetic fields heat that disk to extreme temperatures. As the gas rushes in, it can shine with a brightness that outshines every star in the galaxy around it. From across the universe, that light arrives as a piercing, almost featureless glare, broken only by spectral lines that have been dragged and stretched by both gravity and cosmic expansion. The puzzle that long predated James Webb is simple to state and hard to solve. Some quasars in the early universe seem to be powered by black holes, already weighing hundreds of millions or even billions of times the mass of the Sun. At times when the universe itself was less than 1 billion years old, growing something that massive, that quickly, under the known rules of physics, is not impossible. But it requires nearly everything to go right. There is a natural speed limit on how fast a black hole can grow by swallowing gas. As gas falls in and heats up, it shines. That radiation pushes outward on the infalling material. If too much gas tries to fall in too quickly, the outgoing light becomes so intense that it blows the rest away, like wind scattering leaves. The balance point, where inward gravity and outward radiation pressure match, is called the Eddington limit. Accreting steadily near that limit, a black hole's mass can grow exponentially, doubling every fixed span of time. But even with that furious pace, there are only so many doubling times available between the very first stars and the quasars we see. If the seeds of those black holes were the remnants of ordinary massive stars, the kind of stellar corpses that form black holes of a few to a few tens of solar masses, they would have to begin almost immediately and grow close to that limit without pause. No long quiet periods, no major interruptions, no chronic starvation. A life lived at full throttle, from the first moment to the one we are seeing. For a long time, this was an annoyance at the edge of the models, something that theorists argued about in papers and at conferences. Maybe the seeds were not ordinary at all, but heavy seeds, black holes born already large, perhaps from the direct collapse of giant, pristine gas clouds that skipped the normal star phase altogether. Maybe dense clusters of stars merged repeatedly, funneling mass into a central object. There were many ideas, each with different implications for how the early universe behaved. What Webb has done is turn that annoyance into something more immediate. Its sensitivity in the infrared, the range where the redshifted light of very distant quasars now resides, allows it to find not just the rarest, most luminous beacons, but fainter, more common ones. In its first years of observations, Webb and its partner observatories have revealed a population of what some teams call little giants. Relatively small galaxies in the deep past whose centers already host actively feeding black holes that are, by any ordinary measure, overachieving. In some cases, when astronomers estimate the mass of the black hole and the mass of the surrounding galaxy stars, they find a ratio that is wildly out of line with what we see nearby. In the present universe, the mass of a central supermassive black hole is usually a small fraction of the total stellar mass of its host, a kind of quiet proportionality that suggests they have grown together over time. In some early systems, that balance seems tilted. The black hole mass appears to be a surprisingly large fraction of the galaxy's mass, as though the central engine has sprinted ahead while the surrounding city is still being built. That imbalance is more than a curiosity. It hints that the conventional story galaxies assemble, then slowly feed their central black holes, may be too simple. In at least some places, it looks as though the black holes may have taken the lead, forming quickly, growing fast, and then influencing how the rest of the galaxy develops. The light from the accretion disk and its associated winds can heat and stir gas on galactic scales, shutting down some kinds of star formation while triggering others. If the black hole is ready early, it can become an architect of its own neighborhood. Webb has also begun to uncover objects that blur the line between ordinary distant galaxies and full-blown quasars. In deep surveys, astronomers have found numerous compact, red sources, sometimes nicknamed little red dots, whose colors hint at heavy dust obscuration and intense activity in their cores. When those objects are followed up with more detailed spectra, some show the unmistakable signs of active galactic nuclei, broad emission lines, high-energy radiation, signatures of fast-moving gas swirling close to a massive central object. These are not the flamboyant quasars of older surveys, blasting away so brightly that they drown out their galaxies entirely. They are subtler, fainter, harder to classify from a single glance. Yet they suggest that actively feeding black holes were not rare exceptions in the early universe. They might have been common, hiding in plain sight, veiled by dust and distance until a telescope like Webb could see them. Then there are the lonely ones. Traditional thinking placed the earliest, most massive quasars in the most crowded neighborhoods of the young cosmos, where intersecting filaments of the cosmic web funnel streams of gas into deep gravitational wells. In such dense regions, galaxies can form and merge rapidly, feeding their central black holes with a steady diet of gas and stars. But some of the quasars Webb is now helping to study appear to live in surprisingly sparse environments. With few obvious neighboring galaxies, if a monster is sitting seemingly alone in a quiet part of the cosmic forest, you are forced to ask, who or what fed it? Did we miss the faint companions that once sustained it? Did it form in a way our current imagination has not yet mapped, drawing its food from less obvious reservoirs? Or is our picture of dense and sparse in the early universe too crude to capture the real flows of matter? Layered on top of all this is yet another timing issue. When Webb and X-ray observatories together identify a quasar at a redshift corresponding to a universe only a few 100 million years old, and the inferred mass of its black hole is already tens of millions of solar masses or more, some teams find themselves pushed toward heavy seed scenarios. That is, toward the idea that some black holes were born not as the small remnants of stars, but as already massive objects formed by the direct collapse of enormous gas clouds or other exotic pathways. The idea of heavy seeds is not new. It has been discussed for years as one route to producing early quasars. But with Webb's data, it moves from the realm of speculative convenience to something closer to a necessity in certain cases. When you cannot stretch star formation histories and accretion rates any further without breaking them, you begin to wonder if the story really does start higher up the ladder. Even the way these early black holes feed seems both familiar and unsettling. In some of the systems Webb has probed, The spectra of the accretion disks and surrounding gas look surprisingly similar to those of active black holes in the nearby universe. The physics close to the event horizon, the boundary beyond which not even light can escape, seems to care very little about whether the universe is billions of years old or just emerging from its first few 100 million years. On the smallest scales, gravity does what gravity does. It is the context that feels wrong. The idea that this very mature behavior is happening in such a young cosmos. Taken together, these observations of quasars and early supermassive black holes do not yet form a single, clean story. Instead, they feel like fragments of a larger pattern just beginning to come into focus. There are too many massive black holes, in too many unexpected places, growing too quickly or standing inexplicably alone. There are galaxies whose hearts seem older than their outskirts. There are environments that do not look rich enough to have fed the beasts they host. Once again, the universe is not breaking our equations outright. It is doing something more subtle and, in a way, more disquieting. It is obeying the rules we know, but combining them in ways we did not predict. Pushing processes like black hole growth into regimes we had assumed would be rare or unreachable. And as we watch these early quasars flicker in Webb's deep fields, we are left with a simple, nagging question. If some of the most extreme objects in the universe manage to grow this fast, this early, how many of our quiet assumptions about what is too soon are really just reflections of our own limited sense of time? It is a quiet kind of vertigo, realizing that the problem might not only be with what lives in the universe, but with the stage it lives on. For most of modern cosmology, space itself has been treated as a kind of obedient background. It stretches. Yes, it curves in the presence of mass and energy. Yes, but on the largest scales, we assume it behaves in a simple, almost anonymous way. No preferred directions. No special places. If you zoom out far enough, every region of the universe should look statistically like every other. That assumption has a name: the cosmological principle. It says that, on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. It does not claim that small regions are identical galaxies and clusters form. Voids appear, but that the overall pattern, averaged over immense distances, has no built-in bias. From that principle, and from general relativity, you get an expanding universe that can be described with a simple set of equations. Those equations relate how fast space is expanding at any given time to the amount and type of energy and matter it contains. The rate of expansion today is described by a number called the Hubble constant. It tells you how quickly distant galaxies are receding from us, on average, per unit distance, because space between us and them is stretching. In this picture, redshift is mostly a measure of that stretching. The light from faraway galaxies is not red because they are racing through space like bullets, but because the space between us and them has grown while the light was in transit. The wavelengths get stretched along with space itself, like lines painted on an inflating balloon. For a long time, this framework seemed not only elegant, but robust. Different methods of measuring the expansion rate gave broadly consistent answers. Studies of the cosmic microwave background, the faint afterglow of the early universe, suggested a set of parameters that, when evolved forward in time, reproduced the large-scale structure we see. Observations of distant supernovae, used as standard candles because their peak brightness can be calibrated, revealed that the expansion of the universe is actually accelerating, driven by something we call dark energy, a smooth, pervasive component that acts a bit like a tension in the fabric of space, pushing it apart. Dark energy is strange, but in the equations it is simple. It is often modeled as a constant energy density that does not dilute as the universe expands. Put that into the framework, and you get an expansion history that fits many observations well. Then, gradually, the cracks began to show, long before James Webb. Astronomers noticed that different ways of measuring the Hubble constant were giving answers that did not quite line up. One route relied heavily on the cosmic microwave background, using early universe physics and evolving forward. Another route used local measurements, distances to nearby galaxies, calibrated with pulsating stars and supernovae, then extended outward. The values these methods produced were not wildly incompatible, but the difference was too large to dismiss as mere noise. People called it a tension, not a breakdown, not a catastrophe, but a stubborn mismatch that refused to go away even as data improved on both sides. When Webb entered the scene, it carried with it the potential to weigh in on that conversation. Its infrared sensitivity allows it to observe certain kinds of variable stars and supernovae with new precision, even in dusty regions that obscure visible light. It can also measure redshifts and detailed spectra of very distant galaxies and quasars, extending our reach into epochs previously accessible only as blurred hints. The question quietly hanging in the background is this: when we use Webb to trace distances and redshifts out into the deep universe, does the pattern of expansion it reveals follow the script we have been using, or does it tug us toward a different shape? Thinking about that possibility forces us to confront what we usually take for granted. We often picture expansion as a perfectly uniform stretching, like a rubber sheet being pulled evenly from all sides. In that picture, every large enough patch of the universe tells the same story. If you draw a grid on the sheet, the spacing between the lines grows at the same rate everywhere. There are no special directions, no regions where expansion is quietly faster or slower. Once you smooth over small-scale lumps. But general relativity does not forbid more complicated behavior. It allows for universes where the large-scale expansion is slightly different in different directions, or where the effective properties of dark energy change over time or with location. We do not usually choose those models because, until recently, there was no strong reason to. Simpler models fit the data well enough. Now, with the combined weight of tensions in the expansion rate and the odd maturity of some early structures, a small group of researchers is starting to ask whether space itself might have more texture than we assumed. Not in the sense of dramatic tearing or obvious preferred axes across the sky, but in subtler ways. Perhaps the effective value of the Hubble constant varies slightly with region, or perhaps dark energy is not perfectly constant, but slowly evolving. It is crucial to be careful here. James Webb was not built as a direct meter of cosmic expansion. Its primary missions are to study galaxies, stars, and planets in detail. But the distances and redshifts it measures feed into the larger web of cosmological inference. When it pins down the ages and structures of distant galaxies more precisely, it helps constrain how much time must have elapsed between different epochs. When it refines the properties of standard candles or standard rulers, objects whose intrinsic brightness or size we think we know it, subtly adjusts the yardsticks we use to gauge the universe. There is also the possibility that our trouble is not with space itself, but with our reading of the clues. If we have underestimated how dust affects the light of distant objects, or misjudged the evolution of certain galaxies, we might be inferring the wrong distances, which then feed back into our sense of how fast the universe must be expanding. In that case, Webb's fine spectral detail and broad wavelength coverage might actually heal some of the apparent rifts, showing that the expansion is more uniform than our initial, cruder instruments suggested. But it is hard to ignore the feeling that we are testing the edges of the cosmological principle more directly than ever before. When Webb aims at different deep fields scattered around the sky and finds, in some directions, slightly different populations of early galaxies or quasars, we are tempted to read patterns into that patchwork. Are we seeing genuine large-scale variations? or simply the messy imprint of cosmic variance, the statistical lumpiness you expect when you only have a small number of samples from a vast universe? On human scales, we are used to landscape, valleys, mountains, plains. We are also used to the idea that, if you zoom out far enough to the scale of continents, or the whole planet, those variations average away. Cosmology extended that intuition to the universe itself, assuring us that, beyond a certain horizon, everything smooths out. James Webb does not yet have the authority to overrule that assumption. Its field of view is still small compared to the whole sky. Its deep surveys, for now, are like core samples drilled through a few selected spots in a vast, unknown terrain. And yet, the possibility that those cores might, one day, reveal deeper inhomogeneities is enough to unsettle. Because if space does not expand uniformly on the largest scales, if there are vast regions where the pull of matter and the push of dark energy conspire differently, then our neat conversion between redshift and time becomes fuzzier. Two galaxies with the same redshift could, in principle, belong to slightly different expansion histories, depending on the path light took to reach us. Even more disquieting is the thought that dark energy itself might be a placeholder, a name we have given to something whose true nature we do not yet understand. If what we are really seeing is a failure of our simple model of space, rather than a simple extra ingredient in an otherwise well-behaved universe, then James Webb's measurements are not just refining parameters. They are quietly asking whether the stage directions in our cosmic script need to be rewritten. For now, the official line in the scientific community is cautious. We do not have enough deep, well-calibrated lines of sight to declare that space is misbehaving in any dramatic way. Many of the supposed anomalies may soften as more data comes in and as more careful modeling is done. It is entirely possible that, in a decade, we will look back and see this era as a time when our uncertainties were still large enough to mimic new physics. But sitting in the present, under the faint glow of Webb's findings, we have to live with the ambiguity. We have to entertain the idea that the very fabric of the universe, the thing we have treated as a gently stretching canvas, might have subtleties we have barely begun to map. And that, if it does, then every distance, every age, every carefully plotted point on our cosmic timeline carries within it the possibility of a quiet, systemic error not big enough to erase the story, but perhaps enough to change its meaning in ways we can feel, even if we cannot yet name them. If the canvas itself might not be as smooth as we thought, it is natural to start staring at the largest strokes on it and wondering how they got there so soon. Galaxy clusters are among those strokes. They are not single galaxies, but gatherings of many galaxies bound together by their mutual gravity, sitting in vast pools of dark matter and hot gas. If a galaxy is a city of stars, a cluster is a continent of cities, with invisible infrastructure tying them together. In the standard picture, such structures are late bloomers. The small ripples in density left over from the early universe grow gradually under gravity. Dark matter clumps. Gas falls in. Small halos merge to form larger ones. And over long stretches of time, the hierarchy builds up. By the time you reach the present era, those mergers and collapses have had plenty of time to stitch together the massive, relaxed clusters we see around us. Hundreds or thousands of galaxies orbiting in a common gravitational well, bathed in hot, X-ray emitting gas. Nothing about that sounds fast. It is meant to be the slowest kind of architecture, carved patiently by gravity over billions of years. When James Webb looks out, however, it does not always see a universe that waited politely for its scheduled milestones. In some of its deep fields, and in surveys coordinated with other observatories, Webb has started to reveal structures that look like the embryonic versions of galaxy clusters, what astronomers call protoclusters, at times when, by conservative expectations, only the raw ingredients should have been in place. These are regions where there is a noticeable excess of galaxies close together on the sky and, crucially, at similar redshifts. They are not just random alignments along our line of sight. They live in the same slice of cosmic time. Often, these young structures announce themselves first in images as knots of activity. Several galaxies packed into a small patch. Some already showing signs of intense star formation or active black holes. When spectra confirm that they share similar distances, the realization follows that here is a region where matter has already begun to pool in a serious way. In some cases, gravitational lensing joins the conversation. A massive cluster of galaxies can act like a lens because its combined gravity bends the paths of light passing nearby. Background galaxies, lying even farther away, can appear stretched, smeared into arcs, or magnified into multiple images. By measuring those distortions, astronomers can reconstruct how mass, both visible and dark, is distributed in the lensing structure. Finding strong lensing effects at early times is another signal that gravity has been busy. For a cluster to lens light noticeably, it needs a substantial dark matter halo, not just a few small clumps wandering near one another. In other words, the scaffolding has to be well underway. Some of the structures Webb and its partners have begun to map look, even in their youth, surprisingly mature in this regard. They already host a tangled collection of galaxies, some of them quite massive, embedded in halos that appear dense enough to bend and magnify light from the still younger universe behind them. The mere existence of such a lens at that epoch carries the same faint whiff of too much, too soon that we saw with the overachieving individual galaxies. There is another layer to the discomfort. Clusters are not just piles of galaxies. They are also reservoirs of hot gas. In nearby clusters, that gas shines in X-rays, revealing temperatures of tens of millions of degrees. It is gas that has fallen into the deep potential well of the cluster and been shock-heated on the way. It takes time for enough material to collect, for enough energy to be deposited, for those halos to fill up and light up. Webb does not see X-rays, but it can trace the cooler and warm components of gas and dust in and around young cluster regions. It can measure how vigorously stars are forming in their member galaxies, and whether some of those galaxies are already being quenched, their gas stripped or heated by their crowded environment. The emerging picture, in certain fields, is of ecosystems that have reached a surprisingly advanced stage of interaction. None of this means we are seeing fully relaxed, present-day style clusters in the deep past. What Webb is catching are more like snapshots of adolescence, structures still assembling, but already complex, already exerting serious gravitational influence, already reshaping the lives of the galaxies inside them. And the ages implied, the times at which these adolescent structures exist, keep brushing up against the edges of what our previous models had prepared us for. Again, there are potential escape hatches. It may be that dark matter clumps into large structures more quickly than some older simulations suggested, especially if the small-scale behavior of dark matter is slightly different from what we assumed. It may be that star formation and black hole activity light up the densest regions earlier, making protoclusters easier to spot than expected, biasing our view toward the most extreme cases. It could even be that we have underestimated how easily large-scale filaments of the cosmic web can funnel matter inward. Those filaments, immense bridges of dark matter and gas linking galaxies across millions of light-years, are the highways of structure formation. If they are more efficient, or if early feedback from stars and black holes helps channel gas along them in particular ways, then clusters could build up their cores faster. But somehow, the story keeps coming back to the same feeling. Regions of the universe that, by our gentle narrative, should still be mostly potential are already deep in the act of becoming. There is an analogy here that is hard to ignore. We once imagined the early universe as a flat field with a few small hills starting to rise. Time, driven by expansion and gravity, would slowly carve those hills into mountains, and those mountains into ranges and basins, until the rich topography of the present emerged. What Webb hints at, in some directions, is a landscape where mountain ranges are already well on their way while the cosmic clock still reads early. And as with earlier chapters of this story, it is the combination of clues that matters. Excesses of bright galaxies in dense knots, lensing signals, signs of environmental effects on galaxies that, by their redshifts, should only recently have begun to share space. Each, taken alone, might be dismissed as an oddity or folded into the wide margins of uncertainty. Taken together, they gesture at a universe that was quick to organize itself on large scales. Ironically, this makes dark matter feel more real and more mysterious at the same time. On one hand, the very existence of such early structures reinforces the idea that some invisible mass is orchestrating the collapse, providing the extra gravity needed to build things so fast. On the other hand, if clusters and protoclusters are forming earlier and perhaps more efficiently than expected, it raises questions about the exact properties of that unseen component. Does it interact with itself in ways we have not fully captured? Is its distribution on the smallest scales different from the simple, smooth models we like to use? These are not questions James Webb was solely tasked to answer, but its deep, sharp view has forced them back onto the table. The universe we see in its images and spectra is not waiting patiently at each rung of the hierarchical ladder. It is, in many regions, racing upward, pulling galaxies together into structures that look uncannily like finished sketches. At times when the blueprint was supposed to be barely drawn, standing in the dark, looking at these distant knots of light on a screen, it is hard not to feel that some part of our sense of scale has been gently mocked. We thought of clusters as the end game of structure formation, the slow, majestic gatherings that crown billions of years of quiet work. Webb suggests that, in some corners of the cosmos, that endgame began almost as soon as the board was set. It is one thing to learn that the scaffolding went up early. It is another to realize that, on that scaffolding, the lights came on almost all at once. Stars are not supposed to be easy. To make even one, a galaxy has to coax cold gas into an improbable state. Vast, drifting clouds of hydrogen and helium must lose energy, slow down, and collapse. Turbulence has to be tamed just enough that gravity can win in some regions, while in others, it still rips clouds apart. Inside those clouds, denser knots form, then fragment, then finally ignite nuclear fusion. At every stage, there are ways for the process to fail. In the familiar picture, star formation is a kind of slow, messy negotiation. A galaxy has a certain amount of cold gas. It turns a small fraction of that gas into stars over tens or hundreds of millions of years. Young stars pour out radiation and winds that push back on the gas, and supernova explosions punch holes through the clouds, stirring and heating them. That feedback keeps the process from running away. Left unchecked, gravity would turn most of the gas into stars in a short time. Feedback acts like a brake. Astronomers describe this balance with phrases like star formation efficiency and gas depletion time. Star formation efficiency is, in simple terms, how quickly a galaxy converts its available gas into stars. Gas depletion time is how long it would take to use up the fuel at the current rate of star formation. If nothing changed, in many nearby galaxies, those timescales are long, billions of years. There is a sense of moderation in the numbers. James Webb has started to show us systems that do not look moderate at all. Some of the galaxies it reveals in the early universe appear to be forming stars at rates that, if sustained, would exhaust their gas in a tiny fraction of the available cosmic time. Their light, especially in the ultraviolet and infrared bands, suggests enormous populations of hot, young stars. Emission lines from hydrogen and oxygen in their spectra glow fiercely, like neon signs announcing recent and intense bursts of activity. There is a subtle art to reading that light. Young, massive stars flood their surroundings with energetic photons. Those photons ionize the gas, stripping electrons from atoms. When the electrons find their way back, they emit light at specific wavelengths, producing sharp emission lines. The strength of those lines, combined with the underlying glow of the stars themselves, lets astronomers estimate how many new stars a galaxy is forming per year. Infrared light from warm dust, grains heated by starlight, can provide an independent check, since it traces starlight that has been absorbed and re-emitted. When you apply those tools to some of Webb's deep-field galaxies, you get answers that feel like they belong in a different universe. Star formation rates that, compared with a typical quiet galaxy today, are not just a little higher, but dramatically so. Compact systems that seem to be converting gas into stars with astonishing efficiency, as if the usual brakes have not merely failed, but been removed. These are sometimes called starburst galaxies, because their activity is not steady but flaring. They do not maintain such furious rates forever. If they did, they would indeed consume themselves too quickly. Instead, the picture that emerges is of galaxies that go through episodes, brief, intense periods where they form many stars, followed by quieter phases. Even knowing that, there is something unsettling about seeing such bursts so early. It suggests that the first generations of galaxies did not tiptoe into existence, but slammed onto the scene already in the middle of dramatic episodes of construction. In the glow of those bursts, entire stellar populations could be assembled in spans of time that, on cosmic scales, are shockingly short. One of the unknowns here is the mix of stellar masses in those early bursts. When a new group of stars forms, it does not produce identical twins. Some stars are small and long-lived, others massive and brief. The statistical distribution of those masses is called the initial mass function. In our neighborhood of the universe, it seems to be fairly stable. Many low-mass stars, fewer high-mass ones. In the early universe, under more extreme conditions, that balance may have been different. If the initial mass function was skewed toward more massive stars, a top-heavy distribution, then a given amount of gas would produce more light and more feedback for the same total mass. That could make young galaxies look even more intense than they would otherwise. It could also accelerate chemical enrichment, because massive stars live fast and die young, seeding their surroundings with heavier elements in a relatively short time. James Webb cannot directly count individual stars in those distant systems, but it can look for subtle signatures in their integrated light that hint at the underlying mix. Some spectra suggest that, indeed, the early populations may have been biased toward larger, hotter stars. If that is true, then the already high implied star formation rates may be only part of the story. The very rules of how stars are chosen from the available gas may have shifted in those first epochs, favoring violent, luminous lives over quieter ones. On top of that, Webb's infrared vision allows it to see star formation that was previously hidden behind dust. In many galaxies, especially those going through intense bursts, dust grains can absorb much of the visible and ultraviolet light from young stars, re-emitting it in the infrared. Earlier telescopes, less sensitive at those wavelengths, underestimated the true level of activity. Now, with Webb, some seemingly modest galaxies reveal themselves as powerhouses once their obscured star-forming regions are exposed. This has consequences for our understanding of cosmic reionization. The transition from a universe filled with neutral hydrogen to one where most of that hydrogen has been ionized by starlight and other energetic sources. Before Webb, a common view was that countless small galaxies, each forming stars at a relatively gentle pace, collectively provided the photons needed to strip electrons from hydrogen atoms in the intergalactic medium. Webb's data suggests that the balance may be more complicated. Perhaps a smaller number of extremely vigorous starbursts, in combination with many faint galaxies, played a larger role than expected. There is also the environment to consider. Some of the most extreme star-forming galaxies Webb has found lie in the dense regions that look like protoclusters. There, streams of gas flowing along the filaments of the cosmic web can crash into existing galaxies, compressing their gas and triggering new waves of star formation. Galaxy mergers become more common in such crowded fields, and mergers are notorious for driving gas into central regions, where it can ignite fresh bursts of stars and feed central black holes. In that sense, the impossible-seeming star formation is not happening in isolation. It is woven into a larger pattern of early structure and dynamics. Clusters forming too early, black holes growing too fast, starbursts burning through gas in wild episodes. These are not separate anomalies, but different faces of the same deeper question. Under what conditions does the universe decide to do things quickly instead of slowly? There is a quiet irony in watching this unfold. For years, astronomers spoke of the peak of cosmic star formation, the time when, averaged over the whole universe, stars were being born at the highest rate, as something that occurred when the universe was a few billion years old, a kind of cosmic noon, when galaxies were active and messy, before settling into the calmer rhythms of later times. Webb is now pushing us to admit that some corners of the cosmos may have reached their private noon much earlier, condensing their drama into a shorter window. None of this means that every galaxy formed its stars in a frenzy. Many likely followed more restrained paths. But the existence of these overachievers matters. They set boundary conditions. They tell us what is possible, and they remind us that our previous view, a universe where extreme star formation was a later, localized phenomenon, was shaped as much by the limitations of our instruments as by the universe itself. With each new deep field, each spectrum full of sharp emission lines and strange continuums, Webb is forcing theorists to revisit their recipes. How easily can gas cool in the densest early halos? How do feedback processes behave when the surrounding environment is already crowded and turbulent? Does dark matter clumping on small scales create pockets where gravity simply overwhelms the usual checks, letting galaxies ignite in blinding bursts? These are technical questions, but beneath them lies something simpler. We are learning that the universe, especially in its youth, is capable of moving with a speed and intensity that our comfortable stories did not fully acknowledge. It can build stars in great torrents, not just gentle streams. It can pack the labor of ages into short, luminous episodes. And once you have seen that, the night sky changes a little. Those dim smudges you thought of as quiet, ancient islands were, once, the stage for storms of creation so intense that even our best words for too much, too fast feel suddenly a little small. By the time you accept that the universe was building stars too quickly, another quiet realization follows. Those stars did not stay simple for long. In the beginning, the chemistry of the cosmos was almost brutally plain. Out of the early fireball, as the universe expanded and cooled, only the lightest elements emerged in any real quantity. Hydrogen, helium, a trace of lithium, no carbon to build complex molecules, no oxygen to bind with hydrogen into water, no silicon for rocky planets, no iron for the cores of worlds, or the blood of any eventual animal that might evolve to ask questions about all this. Everything heavier was supposed to be an afterthought, forged later in the hearts of stars. The way we usually tell that story is gentle. The first stars form out of nearly pristine hydrogen and helium. They live their short, brilliant lives, fusing those light elements into heavier ones in their cores. Some die quietly, folding into black holes or neutron stars that lock away part of their chemistry. Others explode as supernovae, flinging newly minted elements into the surrounding gas. That enriched gas cools, collapses, and forms a second generation of stars. Those stars, in turn, add more heavy elements to the mix, and the cycle continues. In that picture, heavy elements, what astronomers call metals, even though the term includes things like carbon and oxygen, grow slowly. Each generation adds a little more to the interstellar medium, the thin gas that fills the space between stars in a galaxy. Over time, you expect a gradient. The oldest, earliest galaxies should be nearly metal-free. Later ones should show more and more, until, in present-day systems like our own Milky Way, a rich periodic table is woven into the gas and dust. James Webb is now peering back into a time when, by that logic, the universe's chemical story should barely have begun. And yet, in the spectra of some very young galaxies, it sees clear, sharp fingerprints of heavy elements that, on first encounter, feel as though they have no right to be there in such abundance. The way this appears in the data is unexpectedly delicate. When Webb's instruments spread a galaxy's light into a spectrum, they reveal thin spikes and dips at specific wavelengths. Those are emission and absorption lines, each corresponding to an atomic transition. Oxygen, for example, produces characteristic lines when its electrons jump between certain energy levels. Neon, nitrogen, sulfur, iron, each element leaves its own pattern. By measuring the strengths of those lines and comparing them with the continuum light from stars, astronomers can estimate the metallicity of a galaxy, a single number that roughly describes how much of its gas is made of elements heavier than helium. They can also look at the ratios between different lines to infer how that gas is being ionized, how hot the stars are, and how intense the radiation fields must be. In some of the earliest galaxies Webb has studied, those line ratios and strengths point to gas that is already significantly enriched. Not as rich as the gas in the Sun's neighborhood, perhaps, but far from the pristine, almost pure hydrogen and helium that naive pictures might lead you to expect. In a few cases, there are signs of oxygen and other elements at levels that suggest not just one, but multiple cycles of star birth and death have already taken place. To get there so quickly, the universe has to squeeze many acts of stellar alchemy into a short span of time. Massive stars, the kind that make the bulk of oxygen and similar elements, do live fast and die young compared with stars like the Sun. A very massive star can burn through its fuel in a few million years. But even if those lives are brief, you still need time for the gas they enrich to cool, mix, and collapse again into new stars. When the light from these galaxies left them, the universe itself was still in what we would call its early childhood. For some, only a few 100 million years had passed since the first atoms formed out of the primordial plasma. Yet their spectra speak the language of a cosmos that has already been busy recycling its material. Again, there are possible loopholes. One is that our expectations for how quickly heavy elements build up in the first galaxies may be too conservative. If the earliest star clusters were extremely dense, and if their initial mass function leaned heavily toward very massive stars, then the rate of enrichment could be faster than older models assumed. Those massive stars would go supernova in short order, their debris trapped in the deep potential wells of young galaxies, quickly seeding new generations. Another is that the line diagnostics calibrated in nearby galaxies may not translate perfectly to the extreme conditions of the early universe. The same pattern of lines that, in a present-day galaxy, would imply a certain metallicity might, under a harsh, hard radiation field from unusually hot stars correspond to a different mixture. What looks, on first pass, like surprisingly high abundances, might partly be an artifact of trying to use local rules in a very non-local context. Even with those caveats, the pattern is hard to ignore. Webb keeps finding signs of early enrichment. Oxygen, neon, and other elements are not waiting politely in the wings. They are already working their way into the gas from which new stars are forming. The cosmic chemical clock, like the star formation and black hole clocks, seems to be ticking faster than we thought. This has consequences for some of the most romantic ideas in astrophysics. For years, theorists have dreamed about the first generation of stars, often called population 3 stars. These would be stars born from gas that contained no heavy elements at all, only hydrogen and helium, without metals to help the gas cool. Those stars were expected to be unusually massive, bright, and short-lived. Some might collapse directly into black holes of impressive mass, providing the seeds for later growth. Others might explode in especially energetic supernovae, lighting up the young cosmos in ways we can barely imagine. Population 3 stars have never been seen directly. They belong to an era that is hard to reach with current instruments. And by the time their light has traveled to us, most of their signatures may be diluted or masked by later generations. But one thing astronomers hope to find with a telescope like Webb was indirect evidence of their presence. Galaxies with extremely low metallicities, spectral shapes that hinted at very hot, metal-free stars, perhaps unusual ratios of certain lines. Instead, what Webb often sees in the reachable early universe are galaxies that already bear the marks of metals, not universally, not in every case, but often enough that truly pristine systems seem elusive. It is as if the pure, early chapter of cosmic chemistry was shorter, or more hidden, than we expected. The moment before metals, the time when the universe's gas was untouched by any previous generation of stars, may have been quickly overwritten. There are hints, here and there, of systems that might come close. Galaxies with very low metallicity, with spectra that whisper of hotter than usual stars. These could be the late echoes of population 3 activity, or environments where new stars are still forming out of relatively unpolluted gas. But the overall impression is that, by the time Webb can see galaxies clearly, much of the cosmos has moved past its chemically innocent phase. On one level, this is just another adjustment. We revise our enrichment models. We tweak our simulations. We accept that the first few 100 million years were more chemically eventful than we once thought. On another level, it feels like a more personal kind of dislocation. Heavy elements are not just details in spectra, they are the stuff of solidity, of planets, of atmospheres that can support complex molecules, of the biology that eventually arises. Realizing that the universe learned to make those elements quickly is a reminder that the path from simplicity to complexity may, under the right conditions, be shorter than we imagined. Not guaranteed. Not easy, but available. There is a temptation, when faced with this, to reach for comfort, to say that, of course, the universe rushed its chemistry. After all, we are here, and our existence selects for a cosmos where enrichment happened early enough and thoroughly enough to allow carbon-based life to form. In that framing, the early appearance of metals is not a surprise, but a quiet prerequisite. Yet James Webb's data do something subtler. They do not hand us an anthropic answer wrapped in a neat bow. They simply show that, as soon as stars and galaxies had the chance to begin the work of transformation, they did so with an efficiency that strains our prior sense of pacing. Elements that once seemed like the late products of a long alchemical journey were, in some places, available almost as soon as there were furnaces to forge them. And once you see that, the narrative of the universe shifts a little. It is no longer just a tale of expansion and cooling, of structures slowly coalescing out of a smooth fireball. It becomes, more sharply, a story about how quickly raw simplicity can ferment into rich complexity when gravity, gas, and time are allowed to conspire, and how often our intuition about what should take a long time is rooted less in physics and more in the limited span of lives like ours. If the universe learned to change its own chemistry faster than we expected, it is natural to ask what that says about the invisible framework that let it all happen. Because underneath the light, there is something that does not shine. Dark matter is, awkwardly, named, it is not dark in the way a shadow is dark, because a shadow is simply the absence of visible light. Dark matter is more like a missing character in a story whose actions are felt everywhere, even though they never step on stage. It does not glow. It does not absorb or emit light in any way we have yet seen. As far as we can tell, it only reveals itself through gravity. The evidence for it comes from places that, by rights, should have been enough. Spiral galaxies spin so fast that, if they contained only the visible stars and gas we see, they would tear themselves apart. Their outer regions rotate at speeds that demand far more mass than the luminous matter can supply. Clusters of galaxies hold together more tightly than their visible contents allow, and the hot gas between their galaxies is too energetic to remain bound unless something extra is weighing everything down. The pattern of tiny fluctuations in the cosmic microwave background, the afterglow of the early universe, encodes the fingerprint of whatever was pulling on matter back then, and that fingerprint matches a universe filled with an unseen component. We gave that component a name and some properties. Non-luminous. Cold, meaning its particles move slowly compared with light, interacting with ordinary matter mainly through gravity. In simulations, such a substance behaves in a way that is both simple and astonishingly effective. From an almost uniform early universe, it collapses into halos, then into a vast, branching network of filaments and nodes, with empty voids stretched between them. This is the cosmic web, the largest pattern we know of, a three-dimensional lace of matter on which galaxies form like dew on a spider's strands. In that picture, galaxies are not scattered randomly through space. They gather along those filaments, flow into knots where filaments intersect, and orbit within the deep potential wells of dark matter halos. The web grows over time as gravity slowly amplifies the initial tiny ripples. Filaments become denser, nodes become more massive, voids empty out. For a long time, that growth was something we mostly saw in simulations and in large surveys of relatively nearby galaxies. Map enough galaxies over enough of the sky, and the pattern emerges: long strings, walls, clusters, bubbles. It is a structure that belongs to a mature universe, one that has had billions of years to lay down its architecture. James Webb, by design, cannot see dark matter directly. Its instruments collect light, not gravity, but it can see the traces that ride along that invisible scaffolding. It can watch how galaxies, even very young ones, arrange themselves. And in a few special cases, it can watch dark matter bend light itself. Gravitational lensing, the bending of light by mass, turns the cosmos into a strange hall of mirrors. When light from a distant galaxy passes near a massive cluster on its way to us, the curvature of space-time around that cluster deflects the light. The distant galaxy may appear stretched into an arc, duplicated in multiple images, or magnified into something brighter than it would otherwise be. The visible galaxies in the cluster and its hot gas contribute to that effect, but so does the much larger reservoir of dark matter. Webb's sharp infrared vision makes those lensed background galaxies easier to see, especially the faint, distant ones that older telescopes missed. That, in turn, makes it easier to reconstruct the mass distribution in the lensing cluster. You adjust a model of where the dark matter must be until the simulated bending reproduces the arcs and smears you actually observe. When you do this for some of the massive structures in Webb's fields, at times when the universe was still relatively young, you sometimes find yourself staring at halos that look too heavy, too concentrated, too early. Again, it is not that they break the laws of physics. It is that they push against the margins of what our cold, dark matter simulations have been comfortable producing at those epochs. To build such a halo, gravity had to collect a remarkable amount of matter into a single region, and it had to do so quickly. The Webb, in those places, seems to have woven itself into thick strands with surprising haste. Beyond the lensing, there is the patterning of young galaxies themselves. Webb's deep surveys reveal that even at high redshifts, where we once expected a more scattered, primitive distribution, galaxies are already showing signs of being organized along filaments and into overdense knots. Protoclusters and groups sit at the intersections, while other galaxies appear strung out in chains that recall the large-scale structures we see much closer to home. In some fields, you can almost feel the web underneath the image, like the grain in a piece of wood, revealed by the way dust clings to it. Galaxies that share almost the same redshift cluster on the sky, as if they have been funneled together by unseen channels. Their properties sometimes vary with environment. Those in the densest knots show signs of more rapid evolution, more intense star formation, or earlier quenching, as if being at a crossing of the web accelerates the life cycle. The uncomfortable part, once again, is timing. The standard picture of cold dark matter predicts that, on the smallest scales, structures begin to form early. But the fully developed cosmic web, the long, continuous filaments connecting massive halos, is something that really blossoms after a few billion years. Before that, you expect the pattern to be less fully sketched, the web to be faint, like pencil lines waiting to be inked. Webb's glimpses suggest that, in at least some volumes, the inking started early. There are possible ways to reconcile this. It may be that earlier, less detailed simulations underplayed how quickly the web sharpens in certain regions. Numerical limitations can smooth over small-scale features, making the growth look more leisurely than it truly is. As computing power improves and simulations include more realistic physics, some of the apparent discrepancies may shrink. There is also the fact that our observations are biased. We tend to point telescopes at interesting places, at hints of overdensities, at regions where previous surveys suggested something unusual. That means Webb's most detailed maps of the early universe are not random samples. They are, in a sense, the highlights, the corners where the universe has already hinted that it is doing something dramatic. If you only ever visited major cities, you might think the whole planet is made of skyscrapers. But even after you remind yourself of that, the impression is hard to shake. The combination of heavy halos implied by lensing, dense associations of galaxies at surprising redshifts, and early environmental effects all whisper the same thing. The underlying skeleton of dark matter, in some corners of the cosmos, was not a hesitant sketch. It was bold, decisive lines laid down fast. That, in turn, nudges uncomfortable questions back into view. Are we certain that dark matter is as simple as we have modeled it? A cold, collisionless sea of particles that only feel each other through gravity? If the small-scale structure of dark matter is slightly different, if the particles have tiny interactions with one another, or if some fraction of dark matter is warm rather than cold, meaning it moves a bit faster and smooths over small clumps, the growth of the web could change. Some of those alternatives have been proposed for completely different reasons, such as tensions in the way satellite galaxies around larger galaxies are distributed. Webb's data adds one more strand to that tangle. There is also the possibility that dark energy, The driver of the accelerated expansion has a more complicated behavior over time than a simple constant value. If the balance between the inward pull of gravity and the outward push of dark energy shifted differently in the early universe than our simple models assume, the timing of structure formation could be altered. Slight differences in that balance integrated over hundreds of millions of years could mean the difference between a filament that is merely outlined and one that is already thick with galaxies. For now, these remain speculations. The safest, the most conservative route is to assume that the basic ingredients are right, but that our approximations in simulations and our reading of observational biases are not yet as refined as they need to be. That approach has served cosmology well in the past. Many apparent crises have softened under better data and better modeling, and yet, Webb's view of the young cosmic web leaves a residue of doubt. We are watching a pattern emerge that we thought we understood from its later chapters, only to find that its opening lines are more emphatic than we expected. The universe seems to have had less patience, even at the level of its invisible bones. There is a quiet, unsettling symmetry in this. The things we can see: stars, gas, dust. Galaxies rush toward complexity. The things we cannot see, dark matter, halos, and filaments, seem to have done the same. The visible and the invisible conspired together, racing ahead of our expectations, laying down a network and filling it with light before our equations were ready to accept it. If the web of dark matter really did grow up too soon in some sense, then the story of the universe is not just one of unexpected brightness, but of unexpected structure. We are forced to admit that even the parts of reality we thought were safely abstract background parameters in a set of cosmological equations may be less sedate than we hoped. And somewhere, beneath the technical arguments about particle properties and power spectra, there is a simpler realization. The universe did not wait for us to be ready before it wove its skeleton. It did not pause to match our preferred pace. It built its hidden highways early, and on those early roads, everything else rushed forward. It is tempting to blame everything on gravity and chance, on a universe that simply rushes ahead faster than we thought. But there is a stranger feeling that creeps in when you step back far enough. It is the sense that things very far apart seem to be keeping time with each other, without any way to talk. From the start, cosmology has wrestled with a simple limitation: nothing can outrun light. That rule is not a detail. It is a boundary. It means that every point in space has a kind of private horizon, a limit beyond which events cannot have influenced it yet. We can draw that limit on a diagram and give it a sober name like a light cone. But underneath the mathematics, the idea is plain. Causality has a finite reach. Look at the universe when it was very young, and those horizons were small. Space was more compact, yes, but light still needed time to cross distances. Regions that now lie billions of light years apart were closer then, yet not necessarily close enough for any signal to have passed between them in the available time. They were, in a real and technical sense, out of touch. And yet, when telescopes like Webb and the observatories that came before it look out across those distances, they find a cosmos that often behaves as though it has read from the same script. The cosmic microwave background, that whisper of radiation left over from the young universe, is almost the same temperature in every direction. Tiny ripples in that glow, the seeds of later structure, have nearly identical statistical properties no matter where you look. Distant patches that never had time to exchange information still appear to share the same initial conditions. That puzzle is old. It is part of what inspired ideas like cosmic inflation, a brief episode of extremely rapid expansion in the earliest moments that could, in principle, have put distant regions into contact before flinging them apart. But Webb is now hinting at a subtler kind of coordination, not in the faint afterglow, but in the later, brighter acts of the play. When it peers into different deep fields scattered across the sky, separated by huge angles, It finds galaxies and protoclusters that seem to switch on at roughly similar cosmic times. In widely separated directions, star formation ramps up, heavy elements appear, black holes ignite, and filaments of the cosmic web sharpen, all within comparable windows of the universe's age. It is as if distant neighborhoods, unable to exchange even a single photon across their young horizons, still manage to hit similar beats. In one sense, this is exactly what the standard cosmological picture predicts. If the initial fluctuations were laid down in a statistically uniform way, and if the laws of physics are the same everywhere, then large swaths of the universe should, on average, evolve in similar fashion. Gravity does not need to send messages from one region to another to enforce that. It only needs to follow the same rules when given similar starting patterns. But when you look at the details that Webb can now resolve, the illusion of a shared rhythm becomes more unsettling. In one direction, you might see a proto-cluster where galaxies are already interacting, forming stars at furious rates, and hinting at a dense dark matter halo underneath. In another, at nearly the same redshift, you find a similar knot, different actors, different local histories, yet a comparable stage of development. In still another, you might see galaxies whose central black holes are just entering an active phase, lighting up as quasars or subtler active nuclei, at ages that match their distant cousins to within narrow margins. None of these regions have ever traded a signal. The time it would take light to cross from one to another exceeds the age of the universe at the moment we are observing in their past. Yet, our models invite us to think of them as parts of a single, coherent storyline, as if some unseen director were calling out cues that they somehow all hear at once. In the mathematics, the explanation is that the director is not a separate being at all, but the shape of the laws themselves. The equations of general relativity, the behavior of gas and radiation, the physics of star formation and feedback, they are local. But they are also universal. They do not need to communicate across space. They only need to be the same everywhere. That is, in many ways, the most conservative, least mysterious reading. But sitting with Webb's images, there is something in the emotional texture of it that feels stranger, because those laws do more than enforce uniformity. They seem to allow, or even encourage, similar complexities to arise in places that will never meet. Think of two distant regions of the young cosmic web, separated by a gap so large that no light can cross between them in the time available. Each region contains its own pattern of dark matter ripples, its own flowing gas, its own seed fluctuations, under the same rules. Those ripples amplify, halos form, gas falls in and forms stars. After some time, both regions produce galaxies with heavy elements, active black holes, and starburst episodes, all within similar ranges of cosmic time. From our vantage point now, those regions appear in different parts of the sky. Their light reaches us along different paths. On a map, we may even color them differently, label them as separate survey fields. But if you put aside the map and think only in terms of process, you are seeing multiple, independent experiments run under the same conditions, each one converging toward comparable outcomes. The coordination, then, is not through communication, but through constraint. The universe is not being whispered to, it is being steered by the narrowness of what is possible. James Webb sharpens that sense of constraint by showing how quickly different parts of the cosmos reach key thresholds. The appearance of chemically enriched gas, the onset of widespread star formation, the ignition of black hole growth, the thickening of the cosmic web, all seem to occur early in many places. There is no region, so far, that Webb has uncovered where the universe has decided to remain simple for dramatically longer than its peers, where galaxies are still in a deep, delayed slumber, while elsewhere the lights are blazing. Of course, selection effects hover in the background. We look where our instruments can see. Our deepest fields cover small patches of sky, and we point them at places that already looked promising in other surveys. It could be that, somewhere off in directions we have not sampled, there are vast volumes where structure took its time, where stars kindled late. For now, those possibilities remain hypothetical. What we actually see are many lines of sight that show broadly similar tempos, decorated by local variations. That is enough to stir a quiet philosophical discomfort. We like to imagine that distance buys difference, that places beyond all hope of contact are, in some sense, radically other. Webb's data hint at a universe where, instead, vast, causally separate domains end up writing similar histories, not because they are connected, but because the space of possible stories is narrower than we thought. It is easy to overreach here, to slide from a sober reading of the evidence into mystical language about purpose or design. There is no need for that. What Webb gives us is not a message about why the universe is the way it is, but a sharper image of how thoroughly its laws can sculpt outcomes in the absence of communication. On human scales, coordination without contact feels impossible. Two people cannot move in step if they never see or hear each other, unless they both follow a third rhythm, like a piece of music played into separate rooms. On cosmic scales, the music is the set of physical laws and initial conditions. Regions of space that never exchange light can still evolve in ways that rhyme, because they are both dancing to the same pattern of rules laid down at the beginning. The unsettling part, perhaps, is not that such coordination exists, but that it is visible at all. That we can, from a small rock in an unremarkable galaxy, look out with a gold mirror and detect similarities in the behavior of systems so remote that, in any practical sense, they might as well belong to different universes. James Webb does not show us a cosmos of perfect synchrony. It reveals plenty of variation, plenty of local accidents and asymmetries. But beneath that, in the timing of key transitions and the rapid rise of complexity across widely separated fields, there is the faint outline of a deeper order. An order that does not care about our intuitions, or about what feels reasonable. An order that holds distant, isolated regions to the same quiet standards, without ever giving them away to compare notes. And as that realization settles, another question forms, not about the universe, but about us. If reality can coordinate itself so thoroughly without communication, if distant volumes converge on similar structures simply by obeying the same silent laws, then how much of what we call surprise is just the moment when we finally recognize a pattern that was there all along, written everywhere, waiting for a telescope sensitive enough to reveal it? In the end, James Webb is just a machine. Gold and beryllium, detectors colder than any winter on Earth. A mirror unfolding in a darkness that does not know it is being watched. It has no stake in what it shows us. It does not care that galaxies appeared early, that black holes grew fast, that stars burned through their fuel as if time were cheap. It does not care that heavy elements, the ones that will one day sit in bones and oceans and nervous systems, arrived sooner than our equations were ready to allow. It simply returns the light as it finds it. We are the ones who feel the fracture when the light does not match the story. We are the ones who have to live in the space between what our models predicted and what the universe calmly insists on doing. We redraw timelines, rewrite formation histories, bend parameters, test new ideas about dark matter and dark energy. And still, there is the quiet sense that reality is slightly ahead of us. James Webb does not answer the largest questions. It does something stranger. It makes those questions unavoidable. It shows us a universe that organizes itself quickly, that grows structure and complexity as soon as it is allowed. A universe where distant regions, forever, out of contact, still move through similar phases under the same set of silent rules. A universe that is not tuned for our comfort, but in which beings like us can arise, build telescopes, and find that the foundations beneath our favorite explanations are less solid than we hoped. Against that, our lives are brief. Our meanings are local. Nothing in the data promises that they matter. And yet, as that ancient light falls onto a small mirror far from home, and is turned into numbers and then into understanding, something undeniable happens. For a moment, in one corner of one galaxy, the universe becomes aware that it does not understand itself. The rest is up to us.